start. So welcome to everybody for a new session of the Logica Universalis Webinar. So today we have a session with some people from Portugal, and the chair of the session will be Carlos Caleiro, who is a member of the Editorial board of Logica Universalis. Carlos.
Hey, good afternoon, everybody. Welcome to this session. Well, one of the already many sessions of this webinar that Jean-Yves took the opportunity to organize in conjunction with all of the other initiatives of Universal Logic project that he started already. Well, not so many years ago, but already a few years ago. I don't know, Jean, 15 years ago, something like that?
Yeah, we started Unilog in 2005.
Yeah, so already more than 15 years ago. So it's a nice environment. And of course, I welcome you all here. So as Jean was saying, this is a session which is more or less dedicated to logic in Portugal, in a sense. Of course, we can just talk about a little bit of that, but precisely to give some context. And before we have the main talk of the day, I would like to introduce you to our colleague Francisco Dionisio, who is going to tell you well, a bit about this Logic Prize in Portugal, about how logic is organized in a country like Portugal, which is not a very big country, as you know, and of course our ideas for the future of logic here. So, Francisco, please, you have the floor.
Okay, thank you very much, and good afternoon to everybody. I'm going to share my screen. Well, I was invited to talk a little bit about logic in Portugal. And what happened is that I contacted people doing logic, and with my colleague and friend, Paulo Guilherme, we used the opportunity to ask what people would think about to have a Portuguese logic society, because we don't have one Portuguese logic society. And what happened is that many people were supportive of this idea. So what I thought is, it's more vielleicht, it is important maybe just to talk a little bit about that, and to say that we are going to have a Portuguese logic society in some time, the time needed to the bureaucratic aspects of this to be filled, because we have enough supportive persons for that. So what I want to talk a little bit is the background, maybe why this Amilcar Sernadas Prize happened, and then to do the job that I was asked to do, was to talk a little bit about logic in Portugal. So the main thing here is that we would like to thank Jean-Yves Bézieux, because there's so many things happening. I don't know, in some sense, because of his initiative. I'm listing some of them here. This Logic Prize, I can click on this and show you a little bit, but the Logic Prize is included in the initiative, a Logic Prize in every country. This is a part of the Universal Logic, movement and conferences. Afterwards, there was the World Logic Day. I can tell you, here in Portugal, the first World Logic Day was celebrated in Lisbon at the Faculty of Sciences, the second also in Lisbon at my institute, Department of Mathematics of my institute, and the next one will be at the new University of Lisbon. I just received confirmation that Reinhard Kahle wants to help organize that. And of course, we are now in the webinar Universal Logic. That is also an initiative of James. So I think he deserves that we thank him for all this. And these are not small things, that some, like the last World Logic Day, there were some hundreds of initiatives everywhere in the world. So this is very impressive. So what I would like just to say is, it's taking, okay, this is our page for Amilcar Sernadas Logic Prize. I would like that Portuguese people know that this is a prize in logic for persons that are affiliated with the Portuguese institutions. And it celebrates Amilcar Sernadas, who was a professor in my group, the leader of my group. And it is a person that we respect very much. The talk of today is one of the winners of this Logic Prize, of the last edition of this prize. There were two ex aequo winners, and one of them is presented today. Sorry. Oh, there it is. Okay. This slide, I think I already said what I had to do, that it is important to have a Portuguese Logic Society. What I want to stress here is that it should include people from all fields of logic, like logic for computer science, for law, for philosophy, for mathematics. And we have people working in these fields in Portugal. And there is this phrase that was just written this morning: this is going to happen. We are sure that we have enough people interested in creating this society. Okay, and now, so what I was asked to do was to describe what is logic in Portugal. We don't have so many people, but we have identified people working in these fields. I will read the titles, but not the centers. I hope that people from Portugal that are included in these centers will be able to recognize their centers here, or their research units here. And okay, so we have people in abstract deductive systems, combination of logics, computability, recursion theory and complexity, logics of knowledge and belief, artificial intelligence and automated reasoning, logics of computation, many-valued logics and para-consistent logic, modal logics, several variations, model theory, non-monotonic logics, non-standard analysis, philosophy and history of logic, probability and quantum logics, proof theory, proof mining and functional interpretation, specification and verification, and type theory. Okay, the people that we identified, of course, some may be missing, working in logic in math departments are, counting them all, we identified more than 55 persons. These are the persons in mathematical departments, these in computer science departments, and there are also people in philosophy and law departments. Okay, that brings us to the conclusion. The conclusion, again, I think I said this already many times, but it is important. We are about to start the a Portuguese Logic Society. The first, a very preliminary step is to have a mailing list with these persons referred before. And in the end, it's my email in case someone that we did not contact before would like to contact me. And that's what I have to say. Thank you so much.
Okay, thank you. Thank you, Francisco. Well, maybe I can just add a comment of my own that I support this initiative with the society, because actually even in a small country like Portugal, people tend to, well, people know each other, of course, but tend to, it's not so easy. We are also busy in doing our little things, that most of the time it's relatively difficult to make bridges with the others. And as we know in science, it is fundamental to keep making bridges with the others. That is one of the lessons also of the Universal Logic initiative that we are also celebrating in a sense. And it was also one of the big contributions among many others of Professor Amilcar Sernadas. I think that was a very important researcher and teacher of logic in Portugal in the last, well, 30 years, I would say. And who was also a person that valued a lot this ability to make bridges to all the other disciplines around that use logic or similar approaches to their work. Okay, I don't know if there are any questions.
Well, I would like to make also some remarks, Carlos.
Yeah, sure.
Saying, well, what is this project of Universal Logic? I developed this project not only by myself, but with the help of many friends and colleagues. So it's very important to emphasize this point. Well, for example, this webinar was organized together with Springer, who is supporting our activities since the start, because we decided to create this journal Logica Universalis with Birkhauser, Springer, and then there's a book series to the Universal Logic, and now we have this webinar. So I was contacted by Angels who is here today, and this at first this was her idea to do that. So I'm very glad with that, and with people also from all over the world. And in particular, since we are talking with people with Portugal, so I met Carlos Caleiro, who is here now for the first time in Las Vegas. I remember that. It was not for gaming; it was a conference, a workshop. And then it was 2001. And then after that, I came frequently to Lisbon to work with this group, made some friendship with Amilcar Sernadas, who liked very much the idea of Universal Logic. And then we organized a third Congress of Universal Logic in Lisbon in 2010. So I'm glad that now there will be a Portuguese Logical Society. And I would like also to say a few words about logic in the history of logic in Portugal, because there is a famous Portuguese mathematician logician, Antonio Monteiro. Antonio Monteiro was one of the founder of the Mathematical Society, Portuguese Mathematical Society. And in 1940, and then he moved for political reason, he moved to Brazil, and then to Argentina, where he founded a very important group of research in Bahia Blanca. So he was Antonio Monteiro was very important for the development of logic in South America. That's it.
Okay, very good. Any further comments or questions? Well, I don't see any raised hands. Okay, so I think this is well, it has been a nice contextual introduction So maybe we can move to the main core of this session, which is the presentation of one of the two co-executive winners of the Logic Prize last year or this year, I'm not sure. This year, which was the first edition of the Logic Prize in 2021, right? So it is, of course, then my pleasure to present to you the work of Paulo Guilherme Santos and Reinhard Kahle, who are colleagues from the Universidade Nova de Lisboa, so the new University of Lisbon. Their work is about the boundaries of decidability in piano arithmetic, or I should say maybe the boundaries of undecidability of piano arithmetic. And so our speaker will be Paulo. So I would like to welcome Paulo, and you have the floor for the next 30-40 minutes for doing your talk. Thank you.
Thank you very much. I will now share my screen. Okay, I believe you can see, right? Okay, perfect. So thank you very much for this kind of introduction and for the opportunity to give this seminar here. And the work I'm going to present is a joint work with Professor Reinhard Kahle. And as you can see by the title, this is a work on k-Provability. And before actually presenting the main results of our work, I would like to start this presentation by settling some important notions. So starting from this, let us settle the following definition. By k-Provability, I mean this notion of provability. That is, the notion of a formula being provable for a fixed theory with at most k-steps. And by k-steps, I mean, for instance, in a Hilbert-style system, the number of lines of a proof. And by the proof skeleton problem, I mean the problem of deciding if a given formula has a proof with skeleton, and by skeleton, I mean the list of axioms and rules that were used in the proof, is the considered one. So the proof skeleton problem asks for an algorithm that has two inputs, namely a formula and a proof skeleton, and the goal of the algorithm is to decide if there is a proof of the given formula whose skeleton is also the given. It is a known fact that k-Provability is undecidable for the sequent calculus of arithmetic, and this fact was discovered by Sam Buss. But in that work, Sam Buss, in his version of the sequent calculus of arithmetic, assumed that first-order logic had an infinite number of binary relation symbols where he had no further axioms on them. So he simply had the opportunity to use them. If one does not assume that condition, the k-Provability problem is not known to be decidable or undecidable in that context. Moreover, k-Provability is known to be decidable for several formulations of piano arithmetic where the universal instantiation schema, this one, is replaced by other schemata. And this is a very simple schema, as you probably know. It stands simply, it expresses simply the fact that if a formula is universally valid, then one can instantiate by any term that is, of course, substitutable by for the variable in the considered form. Yet, it is an open problem whether k-Provability for PA with the usual instantiation schema is decidable, but it is known that the proof skeleton problem is undecidable for piano arithmetic with the usual instantiation schema. And now let me just briefly state what we accomplished with this work. First of all, we characterize some proof skeletons for which it is decidable whether a given formula has a proof with the considered skeleton. And secondly, we characterize some values of k for which it is decidable whether a formula can be proved in k-steps. And by the way, these characterizations are partial, so that's why I use the term some. We characterize some proof skeleton, some values of k. So this does not, on the one hand, solve completely the k-probability problem for PA, and on the other hand, it does not go against this fact that the proof skeleton problem is undecidable for PA. These characterizations are natural in the sense that they simply arise from the given setting of a theory whose axioms are given in a Hilbert-style system using schemata, and they are parameterized by unification algorithms. So for a given algorithm, in the conditions that I will explain in my talk, for a given algorithm, one is able to develop a characterization of some proof skeleton and some values of k. Furthermore, our approach is valid for other theories that extend beyond arithmetic. And the idea that behind this is that these theories, the only condition that they need to satisfy is that they have some sort of a schematic presentation of the axioms. To study k-probability in PA, we introduced an equivalent version to PA that we called PA prime. And I will just briefly mention both PA and PA prime just to fix some notation in this setting. We are implicitly considering a Hilbert-style formulation of Peano arithmetic, for instance, by considering these logical axioms. Here we are only dealing with implication and negation, and we assume that the other connectives, for instance, here the conjunction is defined using this one, and moreover, we assume that the existential quantifier is defined using negation and the universal. These are very well-known axioms, but it is important to observe that these axioms are schematic, in the sense that they do not stand for a very concrete axiom, but they vanish over all formulas and variables, and also terms which satisfy certain conditions. More precisely, let us focus, for instance, in the first axiom. We have this phi, this psi, and this mu, but they do not stand for a concrete phi, psi, or mu. They vanish over all possible variables. So in a sense, these stand for variables that are denoting formulas, and we are going to call these variables formula variables. In a similar way, this X does not stand for a concrete variable. It stands for a variable that is vanishing over all possible variables. So it is a variable. Likely, T stands for a term variable. I'd like also to mention here that in these schematic presentations, some axioms have no conditions, for instance, these first three axioms, but some of the axioms have some syntactical condition on the variables of formulas, terms, and variables. So formula variables, variable variables, and term variables. And by the way, all these syntactical conditions are decided. Okay. We are, of course, considering modus ponens and the generalization rule, as it is common to do in this setting. As you all know, one can develop Robinson's arithmetic by considering these axioms, and PA can be obtained from Robinson's arithmetic by adding this induction schema. And again, this is a schema in the sense that I previously mentioned, namely that we have variables standing for formulas and so on and so forth, and again, a decidable condition. We developed a theory PA prime that is obtained from PA by changing the induction schemata. And here the idea was that we avoided the occurrence of a variable being replaced by something where that very variable might occur. But we did it in such a way that these two conditions are equivalent, namely that the formula is provable in PA using at most k-steps, and the second condition is that that very formula is provable in PA prime using also at most k-steps. So PA prime is not only a version of PA in the sense that it has the same theorems, but moreover, it is a version that respects the k-probability of PA, or at least that standard version of the axiomatization of this. So the general idea of our approach is to attach a meaning to the combinatorial nature of general proof structures, namely proof skeletons. Namely, more precisely, the different ways to combine in a fixed given number of steps the axioms of the considered theory. And as I mentioned in the introduction, we are going to do this at the level of schemata. So for this, I need to formalize what I mean by a schema. And then I need to justify that with our formulations of schema, we do not go beyond what PA can prove. For that, I will start by defining what a proof skeleton is. Then I will move to a definition of a general version of a term. From that, I will develop a general version of a formula, and finally, I will be able to present the definition of a schema. So all these definitions are going to be presented by induction, and we define the proof skeletons as follows. The basis case is the following: AI is a proof skeleton if AI is the number of an axiom of the considered theory, for instance, PA. And by number, I do not mean the semantical entity, I simply mean a symbol. I'm assuming that I have a symbol denoting each possible axiom. And the induction step is very simple, given two proof skeletons, S0 and S1, then MP of S0 and S1 and generalization of S0 are also proof skeletons. And again, here, this simply stands for this array of symbols and this array of symbols. So proof skeletons are syntactical entities. And the intended meaning is clear. So the intended meaning of the number of the axiom is to represent the axiom. And the intended meaning of this symbol is to represent modus ponens, and this symbol to represent the generalization rule from my introduction. Moreover, we say that the proof skeleton S has k steps in it if it has k applications of rules. And of course, this k might be 0, which corresponds to the basis case, namely the axiom k. As I mentioned, now I will define more formally what a general version of the term is, and the term that we use to mention this is term structure, and the definition is the following. Every variable, every term variable, 0 are all term structures, and the induction step reads as follows: given two term structures, R and S, then S, the successor of R plus S, R times S, and this array of symbols are also term structures. And this array of symbols here, we have an array of variables, and also term structures. And this symbol has a two-folded representation meaning, let us say. On the one hand, it stands for itself, so it is an array of symbols that has its entity. And secondly, as you suspect, it represents substitution. So we are also allowed to make substitutions in the usual way, as in first-order logic. Again, I emphasize, this stands for substitutions with the usual properties, but also it is an autonomous symbol. We define inductively now the formal structures as follows. Every formal variable is a formal structure, and moreover, an equality between term structures is also a formal structure. And as it is common in logic, if F and G are term structures, then the following also are, namely F implies G, not F, for all V, F, and this V stands for a variable, and this array of symbols that again represents substitution with a two-folded meaning, namely representing the actual substitution and being a symbol with some autonomous existence. We say that A is an atom if either A is a formal variable, or it is a substitution of this form, or it is an equality between term structures. Now we can define more formally what a general version of a schema is. So we say that an expression of this form, and I will explain further what all these symbols mean, is a schema where these I and J are simply set of indices, and this F is a formal structure with these AIs being F. Now let us look more carefully to this definition. I've just defined what a formal structure is. It's simply a generalization of what you encountered on my introduction. And now let us focus on this right side. This stands for a syntactical representation of the conditions of the schemata from before, namely being a term being substitutable for a variable in a given formula and other possible conditions. These conditions, as you remember from before, might depend on atoms, term variables, and variable variables. We can also generalize, and we did that, these conditions to occur here, not only with an atom, but also with a formal structures. And these symbols stand for a syntactical representation of the meta-connectives. So these connectives, we assume to be different from the ones that we are using on the formal structures, but they have the intended meaning, namely this stands for disjunction, this stands for conjunction, this one stands for negation. And we assume all the classical logic, more precisely, classical propositional logic apparatus on this, namely the Morgan laws and many other properties. And as I said, several conventions were made to operate the schemata, namely on this right side of the schemata. By substitution, we mean a function that makes a schema more precise than it was before, more concrete, let us say, but still on that general level. Being more concrete in what I meant by my previous assertion, a substitution is simply a function that assigns formal variables to formal structures, term variables to term structures, and variable variables to variable variables. So in a sense, it allows a formula variable to be replaced by something a bit more concrete, namely formal structure, and the term variable to be replaced by a term structure. Having defined what a schema is and what a substitution is, we now can define what the provable schemata are. And again, this is done by induction. Namely, every schema that is an axiom is a provable schema. Keep in mind the ones that I presented in the introduction. And now let us look at the induction step. Let us assume that these two schemata are provable. And let us just observe the following. In the blue one, we have a usual schemata from before. And in this red one, I'd just like to mention that we have an implication. G implies H. So let us assume these two provable schemata, and let us assume that there is a substitution such that the image of F under the substitution is equal to the image of G under that very substitution. In other words, let us assume that F, after being made a bit more concrete, has the same shape as G does. So in this context, we say that this schema is provable. Let us see what this schema is. So first of all, at the formal structure level, we have simply the image of the right side of the implication. So this right side. And now we simply add the two conditions that we had before, the blue one and the red one. And we are allowed to add some other possible conditions if we wish to do so. This is a provable schemata, and if we start from a provable schemata and we simply place a universal quantifier, we get a provable schemata. The idea behind the first provable schemata is to represent at the schemata level modus ponens, and of course the second one is here to represent the use of the generalization rule. A provable schema is provable in k steps if in the construction of S as a provable schema were used as most case steps, namely in the previous construction I presented. A provable schema that is an axiom has skeleton equal to the number of the axiom. And if a provable schema S has skeleton cursive S, then the corresponding schema, the corresponding proof skeleton that is in correspondence with the use of the generalization rule is this one, and the one corresponding to the use of modus ponens is this one. So this is just to fix the meaning of these two syntactical. Now I have defined what a substitution is. That was a syntactical substitution. Now I will define what a concrete substitution is. And it is something completely different. We say that sigma is a concrete substitution for the schema if sigma assigns formula variables to actual formulas, term variables to actual terms, and variable variables to actual variables in such a way that this condition at the semantical level is a true condition. So in a sense, a concrete substitution when applied to a schema does what the words mean, in a sense that it makes the schema concrete. We make substitution. Focusing on the schema that I mentioned in my introduction, where I had a phi psi in the move, this corresponds just to go to that schema and picking a concrete phi, a concrete psi in the concrete move. And of course, the conditions need to be satisfied. Now, this theorem that I'm going to show you guarantees that we are not stepping outside the realm of k-Provability in a first-order logic theory. Namely, a formula phi, these two sentences are equivalent. Namely, formula phi is k-step provable in T, and the second condition is there are S a provable schema and there are S a provable schema in k steps and a concrete substitution such that the image of the schema is simply the initial form. This means that k-Provability can be totally expressed using our schema language, and vice versa, the schema language does not go beyond k-Provability. Moreover, given a schema and a formula, we can decide if there is a concrete substitution such that the formula fits the general shape of the schema. Now let us move to our approach. After settling all these definitions, I will say that the proof skeleton S is stable, of course, for a given theory T, if there is a finite list of provable schemata, cursive L, with the following property that we call stability. And this property states that a formula has a proof skeleton is S exactly when there are a schema in the list, in the finite list, and a concrete substitution, such that the image of the schema is the considered form. Moreover, we say that a number is stable, a number k is stable, if all proof skeletons with length at most k are also stable. I will try to explain in a different way what this stability property expresses. It simply states that to see if a formula has a proof whose skeleton is the considered one is the same as having a finite list and go schema by schema of that finite list and try to see if the formula fits that it fits any of the considered schemata. And of course, this can be done in a decidable way, and this is the key feature. It is easy to see that if a proof skeleton is stable, then the corresponding proof skeleton problem is decidable in the sense that we can decide if a formula has a proof skeleton is the stable one. And moreover, k-Provability for stable numbers is also decided. We can also prove that there is a maximum k being a stable number for PA prime and of course for PA also. And so our approach is to now develop concrete lists, to develop a general approach to express concrete lists of provable schemata with this property. Let us move in that direction. And for that, we developed a particular algorithm to guarantee that a general class of algorithms that we considered is non-empty. And now I will focus on the general idea behind the algorithm we developed, and then I will say a few words about the general class. From this reference, we know that second order unification is in general decidable. And the main idea to achieve this conclusion, at least as presented in this paper, is to represent inside the context of second order unification, as usual, numerals, addition, and multiplication. And this can be delivered by equations of this form. And here I'm following the notation of that paper, where this S stands for a unary relation symbol, this array of symbols stands for a substitution, and this circle stands for a binary relation symbol that you can interpret as, for instance, being multiplication. I would like to mention here that in these two previous equations, two important things are occurring. Namely that we have, in the two members of the equalities, occurrences of the same term variable being replaced by something where that very term variable occurs. For instance, here, A is being replaced by S of A. And moreover, we have also occurrences of the same term variable in both sides. We have tau here and tau also here, and the same in the second equation. The algorithm we created is able to solve some systems of this form, where these R's and S are term structure. And by a solution, I mean a common substitution to the left and to the right in such a way that one achieves equality between them. And by substitution, I'm considering the syntactical substitution and not the concrete one. The main move that we made to develop this algorithm was to force the algorithm not to have the needed conditions for the proof, namely conditions of this form. In a sense, our algorithm avoids those conditions, but of course, all this approach has a cost, namely that the algorithm might reject or not even help systems that indeed have a solution. So the algorithm that I previously mentioned, or at least mentioned what the algorithm is able to do, is an algorithm that has the property that I will now mention, namely the property of this general class of algorithms. So throughout the rest of my talk, I will assume that A is an algorithm that is able to solve some unification problems of term structures, of course, for example, by a case analysis, that's a possible approach to it, and with some situations where it might output the word problem. And this might correspond to a situation where the algorithm identifies the conditions of the proof of the paper from 88, namely conditions of this form, and the algorithm simply outputs problem and does not proceed from there. We assume that A also gives information about the conditions needed for each step in the context of provable schemata, for instance, identification of variables, identification of terms, and so on and so forth. But more importantly, we assume this property, this subproperty. And this is the main reason why we needed to develop the algorithm that I previously mentioned. And this subproperty reads as follows. If A is successful for this system, and by being successful, I simply mean that the algorithm helps and does not output problem in any of its computations. And furthermore, if there are concrete substitutions to the left and to the right, such that one achieves equalities, then one needs to, in a sense, be able to factor out the concrete substitutions by means of a syntactical substitution. More precisely, we need to be able to guarantee the existence of a solution that the algorithm outputs and the concrete substitution such that these equalities hold. And again, I emphasize here that in a sense, we factored out these syntactical solution, that must be one of the solutions that the algorithm outputs. From here, we developed for each algorithm a finite list of provable schemata that we denote in this way, and of course this list also depends on the value of k, and also a finite list of proof skeletons that again depends on the algorithm and on the value of k. We say that the proof skeleton is grounded for the algorithm A if this proof skeleton is in this list, where this k is the number of steps of the proof skeleton. Moreover, we say that k is a grounded number for the algorithm A if all proof skeletons whose number of steps is at most k are also grounded for the considered algorithm. And I will denote the union of these classes in this way. Now, the main result of our paper. First of all, given a grounded proof skeleton for the algorithm A and the formula S, it is decidable whether there is a proof of phi whose skeleton is the considered one. So in a sense, this means that the proof skeleton problem for grounded proof skeletons for a particular algorithm A is decidable. And of course, this characterization depends on the algorithm A. If one picks a different algorithm, one might, and indeed does, have a different class of proof skeleton. For k, a grounded number, the following holds. Phi is k-step provable in T exactly when there are a schema S in this list and a concrete substitution such that the image of the schema is the considered formula, and this k here in this list is the same, of course, as the k that one is considering in the k-step probability. This means that for a particular grounded number for an algorithm A, the k-step problem for that particular k is decided. And this is the theorem that I just mentioned. Moreover, we can conclude that, in particular, given a k grounded number for A in PA prime, k-provability for PA prime is decidable, but using the theorem from the introduction, sorry, from my second section of this talk, we can conclude that the k-provability problem now for PA, not PA prime, is decidable for grounded numbers k for, again, a fixed algorithm A. This other theorem that I'm presenting here is also important because it emphasizes that this list with the increment of k keeps adding more information. So in a sense, this means that given an algorithm A, this union of the list is infinite. So we are adding information at each step of the construction of the list. In other words, we are not trivializing the problem. There is no step where the trivialization step occurs. Moreover, we can abstract, and this is my last result, we can abstract the algorithm from our previous construction in the following sense. For each algorithm A, we can create a general algorithm that depends on A with the following property. For every grounded proof skeleton S and every formula phi, the algorithm helps and accepts for S and phi exactly when S as a proof skeleton is S. So this means that all our construction that depended on a fixed algorithm A can be abstracted from that very algorithm. So we can develop a general algorithm to each one inputs a particular algorithm with the properties that we mentioned, namely the subproperty, that decides the proof skeleton problem for grounded proof skeleton. And this concludes my talk. Thank you very much for your attention.
Well, many thanks, Paulo. We have now time for questions. So I would like to ask anyone wants to ask a question to raise their hands. I can ask actually a couple of, well, actually, I think there are three things that I'd like to ask, but very small ones. So you, to start with, you changed your piano arithmetic to a piano arithmetic prime, right? But you did not really explain why you needed to do that. So I presume it has something to do with your notions of stability and groundedness and so on, but maybe you can comment on that. Let me just ask the three in a row, and then you comment on them. So the second thing is whether you have, I presume you should have concrete examples for given algorithms, for given basic unification algorithms, if you have concrete examples of skeletons that are not grounded, or numbers that are not grounded, of course. And I would like to ask you whether deciding whether a skeleton or a number is grounded is itself decidable or not. So, because it seems important if you really want to decide something, maybe you can ask that, but for that you need to know if the skeleton is grounded. So maybe you can comment on these things. Thank you.
Okay, thank you very much for your questions. Starting, of course, from the first question. Yes, it has to do with what you mentioned, and there is another factor to it, namely let me just go to that slide, namely that one second, namely this paper. Because here I mentioned that second order unification is undecidable, and two key factors were the fact that we had the occurrence of the term variable in the two sides, and the term being replaced by something where that very term occurs. If one goes back to the induction axiom, it might be the case that one is in fact substituting a variable by something where that very variable occurs. That's what I needed to avoid. So I developed PA prime where that situation does not occur. I studied PA prime, and then I argue, okay, PA prime is a step equivalent to PA, and so this also works for PA. That's the reason why. Now the question about being grounded, I believe we cannot decide it because if we let us think counterpositively, if we're able to decide it, then we were able to decide the proof skeleton problem, and we know that cannot be the case. So this means that we are almost in the very boundary of the decidability property. Regarding concrete examples, we developed the algorithm I mentioned, but I have some characterizations of case, but I have not actually computed the concrete case, because as you can see, all this notation is really hard to express, so I have not had the opportunity to implement all these factors, but in fact I intend to do so. Thank you very much for your question.
Okay, thank you. So I see a raised hand. Okay, so it's Alexei. Alexei, are you there?
Yes.
Please.
Have you investigated the complexity of your algorithm? I mean, algorithm A. What's the complexity or complexities?
Well, I have not studied it, but I can say right away that it's far from optimal. It is most probably super exponential on the size of things. It's far from being optimal. At this step, I was the main focus of our work was to.
It was not the purpose. It's just curious.
No. We have no idea on the complexity. But again, that's an issue that we also want to study.
Thank you.
Thank you very much.
Okay, so any further questions? I don't see any raised hands. Okay, I have Jerry. Jerry, you there?
Yes, I'm here.
Okay.
I first thank you for this excellent lecture. I am absolutely fascinated by it. It seems to be a major contribution to the understanding between the formal logic, as you presented it, and the chemical sciences. Now, I have been involved for several decades in trying to develop a formal logic for chemistry and biology. And I find the language you use in terms of grounding of logical symbols and the difficulties in substitution to be very similar or analogous to the sorts of logical operations used to explain chemistry. That is, in the context of logic, how atomic sentences become molecular sentences. So I look forward to reading your paper and studying it in detail, but that's about all I can say at the moment, other than that the atomic numbers do not admit substitution. That is, you cannot substitute chlorine for fluorine or similar semantic substitutions. Each atomic number is a constant, a numerical constant, which is subject to operations that changes the identity of the constant. So I have to stop there because that's the limit of my thinking at the moment, but I find it to be very exciting and I think of quite substantial scientific importance within the logic of the natural sciences. Thank you again.
Thank you very much for your very kind words. I also look forward to reading your papers. That's marvelous, the connection you mentioned. I'm really interested to see. Thank you very much.
You're welcome.
Okay, thank you. So any more questions, comments? Well, no, I don't think there is anything else. So if I'm missing something, please tell me. But otherwise, I think we already had a good discussion. These are very nice results indeed. So and of course, it honors the Logic Prize, Portugal, and this webinar too. So I think this was a good session. I don't know if there is any further formal procedures that we need, but if not, I think we should thank Paulo for this very nice talk.
Thank you very much.
And of course, thank also Reinhard for his part of the work, of course. And maybe in that case, we can close this session. I don't know if Antje or Genevieve want to say some final word. Otherwise, thank you all and see you next time.
Okay, Carlos, thank you very much. So it was a very nice session, and we'll have the next one. We have 2 sessions per month. And the next session will be next week with Amilcar talking about Lewis Carroll logic. So everybody's welcome to attend. Hanch, you want to say something?
Just thank you all for joining and thanks for the talk and the presentation.
All right.
See you next week.
Okay.
Thank you. Bye-bye.
Thank you. Bye-bye, everybody. Thank you. Thank you all.
Thank you. Thank you.
Bye-bye.